Hey, Dr. Clark, let's take a look at some of the ideas behind statistical inference for paired data. So the idea, again, with paired data is we have quantitative data and the data is paired. So there's two observations, but there's a natural pairing between the observations. So, before and after, or it's the same person measured twice, that kind of thing, where there's some natural pairing between each measurement, but there are two measurements. And so what you might wonder is, well, why don't we just treat it as independent data with two groups? So you have the mean of one group and the mean of the other group, right? You got two measurements, two sets of data, an X bar for one set of data and an X bar for the other set of data, and then we just compare those X bars to each other to see if they're different or not, right? And that was what we learned in Chapter 6. Well, it turns out that if data is paired, it's better to treat it as paired data because generally speaking, the statistical inference is stronger when the data is paired. So instead, you're going to look at the differences, which means you really just have one set of numbers because you took your pair of numbers and subtracted them. So now you just have, instead of an X bar for data set 1 and an X bar for data set 2, you really just have an X bar for the differences. Okay, so it's almost like a one variable operation instead of two variables. Okay, so when you do a confidence interval, instead of the difference in the means, right? The difference in the means, it's a confidence interval for the average of the differences. So we call that mu d versus mu1 minus mu2. And an example that we started last time with this lyrical music versus instrumental music, can you memorize more words depending on what kind of music is playing? So here's a set of data I got from a previous study where they played instrumental music and saw how many words that they could memorize, and then they played lyric music and see how many words they could memorize. And you can see that this is student 1, they memorized 7 words and then 10 words. Student 2 memorized 9 and then 6, 5 and then 5, 8 and then 9, 7, 7, 9, 8, etc. So you can kind of see, you could treat this as two independent groups, which would be a Chapter 6 method with two means. But you could also just subtract this. 7 minus 10 is -4, 9 minus 6 is 3, 5 minus 5 is 0, and look at the differences, and then you have just a one set of data for differences. And what I want to do is show you how that would look in the applets if you treated it as paired data versus treating it as two independent groups. Okay, so first, if you treated it as two independent groups, you're really in multiple means, Chapter 6. And this would be the data here. I just pasted it in. Here's the box plot for lyric music and the box plot for instrumental music. You can see that the mean here looks like it's bigger than the mean here. In fact, it is. It's 7.3 words memorized for instrumental music and 6.2 words for lyric music, which means that people memorized on average in the sample at least about 1 word more in the sample than they did with instrumental music versus lyrical music. But is 1 word more, is that statistically significant? Well, to see if it's statistically significant, we could take all these words memorized and randomly deal them into two piles, and then if we did that, we would get two piles every time. Each time we did that, we'd get a mean of the one pile and a mean of the other pile. We could subtract those means and plot it into a null distribution and see how often did it happen that it was at least 1.07. And in this case, it looks like we got 0.02. Okay, so that was our p-value. So it seems unlikely that the difference we observed here could be due to random chance. Although 0.02, that's strong evidence, but it wouldn't be very strong evidence, right? So this is the standard two-group Chapter 6 method. So let's see what happens if instead we just paired the data. So if you go to the matched pairs applet right here, and you paste in the data right here, I just pasted in the data, what it will do is it will graph the two dot plots for you. but then it will subtract the numbers and give you the differences. And what you can see here is that almost all the time, people did as good or better with the instrumental music versus the lyrical music. Only 3 people did better with lyric music. And so what that means is when we go to randomize here, what it's going to do is it's going to take all of those numbers that we got, and for each one, so this -1 here, it's going to flip a coin to see if it should keep it as -1 or flip it to +1. So it's essentially saying, hey, what if we didn't know which way the difference went? And they do that for all of them. When you do that, some of the differences would be positive, some would be negative, and you could plot out essentially what would be X bar of the differences. And then we can see how frequently did it happen, as extreme or more extreme as what we saw in the sample. Well, now our p-value is 0.01. So what happened here is the p-value before was 0.02. Now the p-value is 0.01. So apparently the pairing of the numbers gave us stronger evidence. So when we treated the data as paired data, we got a stronger evidence. So now we have very strong evidence versus just strong evidence. And that's kind of the point of doing paired data, is you typically get stronger inference when you treat it as paired data versus not paired data. Okay, so that's kind of the very quick intro to what does inference for paired data look like. In the next video, we'll do a longer example with a little bit more details and the different steps and that kind of thing.